Of course, by now we know what a sensor is. This slide is on the start of every one of my PowerPoints. So we've looked at position sensors, we looked at speed sensors, we looked at weight sensors. We haven't looked at counters because those are actually electronic devices. We looked at pressure sensors, we looked at temperature sensors, we looked at light sensors, liquid level, motion. We looked at proximity, and so these are the ones. So today what we're going to do is we're going to look at flow. Like I said, there's really no way that we can get through all the sensors that y'all came up with back at the very first of the semester. But all you have to do, guys, all you have to do, if you want information about a certain type of sensor, now all we have to do is just go to the internet and type in thickness sensors, or type in viscosity sensors or moisture sensors, and you'll get a lot of different people that make them, and then data sheets and all kind of stuff. So the internet has really helped us as far as finding information about things that we need, and also sometimes about information we don't need. So units of measuring flow. Of course, we have the International Standard Unit, which is liters, which is standard, and flow is measured in volume. So it's measured in volume. So to calculate the volume, it's going to be, the meter squared when you measure it out, and square roots, right? I'm sorry, squared, because you got to have length, height, length, and width to calculate volume. So standard liters per minute. So a liter is a volume, right? Then we have cubic meters per second, and this is the way it would be abbreviated. So this is the volume per second. Standard cubic centimeters per second would be centimeters per second. So those would be the SI units, or the International Standard Units. And the U.S. customary, what we use is gallons per minute. So a gallon is a volume, and then we move a gallon past a certain flow, how fast it moves. So it's volume over time is what it is. So of course we have gallons per minute. So if you ever look at a compressor, that's what it's rated at. In fact, most compressors are rated in something called standard gallons per minute, because the rate of flow varies with altitude, excuse me. So compressors are rated at sea level, or 14.7 psi. That's what they're rated at. How many gallons they can move, how many gallons of fluid they can move in 1 minute. And then we have cubic feet per second. So these are U.S. customary. This is what you'll run into unless you're working at a company that's who's home ported in a foreign country. So basically, we know the basic makeup. So to sense a pressure, what we have to do is we have to use that formula that we've used before, where force is equal to area times pressure, right? So if we take that and put it in our world famous little three expression formula thing, then we know that pressure would be equal to area, force divided by area. So what we do is all our pressure sensors, all our flow sensors are going to have some type of mechanical element out here sensing that. A couple we'll look at actually gives us a digital output, which we could count over time. But some of them are going to use actually a pressure sensor. It's going to sense the pressure, convert it into a force, then compensate for the area, like the tension of a spring or something like that. Then it's going to output a physical movement. Then we're going to have to run it through a transducer. And what's a transducer?
Don't it step up voltage, or is that what it is? Or am I wrong? No, I'm wrong. It's something else.
Well, so what's a transducer? So we talked about this way in the first. We know a sensor is a transducer, but a sensor, but a transistor don't have to be a sensor. A transducer is some type of unit that takes energy in one form and translates it into another. So like a windmill would be a transducer. Yeah, a turbine would be a transducer. So a turbine takes, like we generate our power, takes water moving through a turbine to turn a generator, and it generates electricity. So a sensor is a transducer, but a transducer does not have to be a sensor. So like I say, a Ford is a car, but a car don't have to be a Ford, right? So a transducer, so a lot of our sensors have these transducers in them, which means we take energy, we take a pressure, and then we convert it over to an electrical output, which is what a lot of our sensors do. And then signal conditioning would be if we want to make it digital or we want to make it analog, so that would be this. So these are typical flow gauges. So these are all analog. Of course, a lot of them now would be digital, but even if they are digital sensors, they still use basically the same type of sensing elements that we're going to look at. So these are mechanical gauges. So fluid, a lot of people, when we talk about a fluid, and I was under this impression for a long time, is a fluid, we instantly think of liquids. But that's not true. So this is the definition of a fluid. It's a substance that has no fixed shape and yields easily to external pressures. So these are both gases and liquids. So gases are fluids and liquids are fluids. A substance as a liquid or a gas that is capable of flowing and that changes its shape at a steady rate when acted upon by a force tending to change its shape. So a fluid is basically anything that takes the shape of whatever you put it in, right? And it flows easily. We can make it flow easily by creating differentials of pressures. So like I said, and so when we talk about fluid power, that's pneumatic. The two types of fluid power we use is pneumatics and hydraulics. But I was under the impression until I got into college and started taking courses in this that a fluid was a liquid. Flow sensors. So we have the type of flow sensors that we have are based either on differential pressure, so they measure a pressure on an input and an output, and the differential pressure would change depending on the flow of the fluid. We have a rotometer, which we'll look at. We have a spring and piston. We have turbine, paddle wheels, vanes, magnetic flow meters, and ultrasonic flow meters that we'll be looking at. Now, is this all of them? No, but this is all of them that I could research. So just because you get out there, you know what a flow meter is going to do. It's going to measure the flow of a liquid, how fast the volume is moving over time. And then if you needed to get the actual sensing element, and we didn't cover in this class, and you could always look it up on the internet, right? So this is a pretty simple one to figure out how it works. So we have a calibrated spring, and then the flow comes in, pushes against a plate that's a certain size, generates a force generates a motion, the motion is acting against a calibrated spring that's calibrated according to the surface area, how far it deflects, and it's got this indicator on the side. How far it deflects would be a representation of the actual flow rate. Are we okay? That makes sense? Pretty simple how that one works. This is probably these are probably the most popular we use. So what we do is on this one is we have an orifice plate, which looks exactly like a washer. So you can actually see it right here in this. Let me change colors because that blended in. So here's the actual orifice plate in this You can see the hole through it. So what happens is when the fluid flows, it goes down. The speed increases because it's going through a smaller area, which creates a high pressure on this side and a lower pressure on this side. And the pressure differential is equal to the rate of flow. So the faster it flows, the bigger the pressure differential. The slower it flows, the less the pressure differential. And then what we would do, our actual sensor would be here. Would be there. And it would look at the pressure differential, and the pressure differential would be equal to the rate of flow. Well, it would be proportional. Let's rephrase that. It would be proportional to the rate of flow. So then our sensor would have to compensate for what that, we'd have to come up with that transfer function, right? That's usually built into our sensors that would take the proportional measurement and then convert that into an actual measurement. This is basically what we use over in our both our manufacturing lines. Actually use this technique to generate a vacuum. So it's called a Ventura. So what happens is this is a little more efficient than this, because what happens with the orifice plate is going to create a lot of turbulence right in here. Ventura has a tendency not to produce that, but what happens is it comes over here, it goes down, speed goes up, pressure goes down, and then it comes back and expands back out. So when the speed goes up and pressure goes down, this pressure down here a lot of time is actually a vacuum. And what is a vacuum? In there two M's? I'll get it. What is a vacuum? Nobody knows what a vacuum is. I think it's an E. Nobody knows what a vacuum is. So any pressure below 14.70 psi. So on gauge pressure, if you had a gauge that was measuring gauge pressure, the gauge pressure is sitting at 0 at 14.7 psi. And then if it goes below that, this would be a vacuum. Now, perfect vacuum would be when we've evacuated everything, and that's real hard to produce. So both of our suction cups over on the Festo line and also on the Amatro line use this technique. They just don't have this guy right here. So what it does is it pushes it through a Ventura, which makes it less than 14.7 psi. We got a little suction cup out here. This guy is below 14.7 psi. This guy out here, here's my plate. This guy is greater than 14.7 psi. That's going to generate a force which holds it in. So it's not the vacuum that's holding it. It's the 14.7 psi that's pushing on everything else. That's actually holding it in, which is pretty interesting. So vacuum creates a negative pressure, which is below 14, negative gauge pressure, which is below 14.7 psi, and then the external pressure is what's holding it in there. But on a flow meter, we use the same thing that we did on the orifice. So over here, this would be a high pressure. This right here would be a low pressure. And then we come up here and bring this into our sensing element. And of course, the sensing element would give us this would give us a pressure differential that's proportional to the flow. And of course, your sensor would actually be calibrated for the transfer function. Some flow meters basically has a dial that you can actually adjust the flow. So this is a Venturi. So you can actually see this big old pipe, and then it drops down, goes to the Ventura, and then actually comes back up. So here's the actual Ventura right here, and then this we would mount it with a flange right there. This is what airplanes use. They use a PDOT static. So basically what we do is we have a static, and on the airplanes that I worked on, the actual static tubes was mounted on the side of the plane. You like my airplane? And then ours had a Mad Stinger on the back. So, and then the PDOT tubes was mounted up here. And our planes had 2 of them on there. I'm laughing because, you know, what's that? The Boeing 737B, or whichever one the one that was crashing because of the PDOT static tubes. They had a failure in the angle of attack, which was basically the same thing. But the angle of attack basically had a little vane on it. Ours was mounted on the side of the plane. And then, of course, the air flowing over it would tilt depending on the attitude of the airplane. And Boeing had a problem with theirs, and they did not have a backup system. So when it failed, it would tell the autopilot that was flying the plane. So people don't understand. When I was in the Navy, the pilots landed the plane, and they took the plane off. But most of the time, the plane flew on autopilot. Well, what the planes do now is they take off and land basically with autopilots. So what would happen was the plane would tell the angle of attack was telling the plane it was going to stall because it thought the nose was up too high, and it would dip the nose down, which would cause the plane to try to pick up speed. And y'all know the story about that. So ours, we bring in pressure, then we compare that to a static pressure. And what was nice is that this made it work even at higher amplitudes, because what would happen would be when you went up, your static pressure would go down and your PDOT pressure would go down, but the difference would still be an indication of how fast the plane was going, which was basically a flow indicator, you know, how fast the air's flowing over the plane. So, and of course we had other methods of sensing speed, but this was the last method that they would use if something else happened to all their other speed indicators. They had Doppler, all kind of stuff that was on our airplane. So what happens is we have a static pressure, and then we have a dynamic pressure, and then we compare the two. So what this is, it doesn't change. We get an accurate measurement even if the viscosity of the liquid is big or high, or if it's low, you still get the same thing because it's comparing the two pressures between what's flowing. And that's what was nice about this on an airplane, is that no matter how high you was flying, you could be flying at 35,000 feet, and your PDOT static system still worked, because the PDOT pressure would go down, the static pressure would go down, and the differential would still be the speed. Our PDOT static tubes were heated. Of course, these have to be heated because you get up to 35,000 feet. It's very, very cold up there, and the PDOT static tubes would freeze up on them. So our PDOT static tubes actually had heaters in them. So there's a story behind that I'm not going to tell. But they'd have to cover them up when the planes were parked, because dirt daubers, y'all know dirt daubers like to find little holes, and they would climb into PDOT static tubes and build their webs, so they had to keep those things covered up. So, and they'd have to check them, and sometimes they'd forget to take the covers off, and they'd turn the heaters on to check to make sure they was working, and they would burn the cover up. So, anyway, rotometer. This basically has to be mounted vertical. And basically what you do is you have a flow that comes in, and then you have gravity pulling down depending on the size. And wherever those things equalize out, the pressure or the force created by the flow, so the pressure is proportional. In fact, you can look this guys up. The speed of a fluid generates a pressure when it strikes up against anything. And of course, that's why we're in big concern about what they call straight line winds. So a lot of people think tornadoes are the only thing that tears up houses, and that's not true. It's the speed of the wind that comes in and strikes the side and all that area on the side of your house and on trees and stuff. This is what gives us problems. So basically, your house is acting like a rotometer out there, where you got gravity holding it down, and then wind strikes it. It generates all that pressure up against the side of your house, and sooner or later, that pressure, the force. If we have pressure, we have force, right? And force is equal to area times pressure. And of course, pressure goes up as speed of the fluid goes up, which starts generating a lot of force. And then your house, the roof of your house, is like this. So what happens when that hits that, it creates a flow, which creates a low pressure. Down here you have high pressure, low pressure. So this is why a lot of times the roof of the house will just take off. You ever seen that on the weather? So it's working like an airplane wing is what it's doing. So this is why you don't see flat roofs get blown off. They're always these angle roofs. So a rotometer, these guys right here work really well. They're very, very cheap. This is about the only one I've got, and you can't see the flow meter. So my flow meter set is very limited. In fact, this is only the one I've got, and this works on the same basic principle. As it switches over. So this, let me get up here. So this is the pressure gauge, and then this right here is the flow meter. So works on the same principle. This has got a metal ball in it, and when the flow comes through the tube, then this is labeled in cubic feet per hour. This actually came off a swimming pool, by the way. And but the weight of the ball, the rate of the flow, will cause the ball to come up, and of course that would be an indication of your actual flow rate. So this came off a swimming pool, and that's the only flow meter that I have. So this is used a lot in fluid power, where we actually have just a vane. The vane is working against a calibrated spring that gives us the math for our flow rate, right? I'm sorry. So I think I solved for the wrong thing a while ago. So I solved for pressure a while ago. I should have solved for flow. So pressure. So area times pressure would determine the force. The force would come up here and actually move the vane. I'm sorry, it comes in this way. Move the vane would deflect depending on how much flow we had. So every one of these so far has used a force to measure the flow rate. So, this one would be digital. So what we have here, or it could be analog, depends on what this thing is turning. This is called a paddle wheel. So this is pretty obvious the way this works. Flow comes in, strikes one of the paddle wheel spins, the rate it spins would give us the indication of a speed. We could have this turn in a tach generator, or I think this one, what it has is it has little magnets out here. And this would probably be a Hall effect sensor. And so the paddles come flying by. Every time the magnet passes the Hall effect sensor, it would generate a pulse. We could come in and count the pulses, and then that would give us an indication of the flow rate. So this is called a paddle wheel, and the next one works on almost exactly the same principle as this one. This is called a turbine type. Works very, very similar to the paddle wheel. But over here, the wheel is perpendicular. Here, the prop or propeller is parallel with it. So the flow comes in, strikes the turbine. The turbine comes up and spins. The rate of spin would be directly proportional to the rate of speed. This has the magnet right here. This shows the Hall effect sensor. So this would work similar to the other one. So the difference between a paddle wheel is perpendicular, and then of course the turbine would be in parallel or in line with the flow. So this one's pretty simple to see how it works. So this would give us a digital output, and of course we could bring this into a programmable logic controller, and then the programmable logic controller could do the math to take care of the transfer function. This could come in, this gives us a digital. What's nice about these is they don't have to be converted into digital to bring it into our main controller that we have in most systems now. So our main system now is going to be a programmable logic controller, is going to take this input, and then of course we could bring this into a counter over time, and we could figure the math formula and actually figure out how to get a flow rate from this guy. And this is digital too. This one's interesting. This one works on the principle of induction. So what do we need to get induction, induce a voltage? We need three things. So what three things do we need?
Rotation, magnetic field, and a conductor.
Well, not rotation. We got to have motion, but that's good. So we have a magnetic field, which would be the first one, right?
Yeah.
I know you knew what you was talking about. Then we have to have a conductor. And three, we have to have what we call relative motion, which one of them's got to move. Yeah. Either the conductor's got to move through the magnetic field, or the magnetic field has got to go through the conduction. So here we have a magnet. Here we got some type of fluid that basically has conduction characteristics. It don't have to be a conductor. So it can't be insulator, you know, and there's very few fluids that don't have some type of conduction characteristics. So what happens when the fluid moves through here, it goes through the magnetic field. The magnetic field induces a small voltage a small voltage into this. This comes over here and flies through this, induces a small voltage into this. So I said that kind of wrong. The flow kind of absorbs the magnetic field, causes the magnetic field to shift depending on the flow rate, and that shift in magnetic field would be picked up by these sensors on the side, and it'll give us a V out that's proportional to rate of flow. You'll probably wonder why I always walk wired at an angle, because I'm coming across my keyboard. So I can't have access to my keys if I flip this thing around and use it like a tablet. So this computer can be used as a tablet. But if I do that, that means I can't use my keyboard to switch between applications. So that's why I'll always write it almost at an angle. So what advantage does this guy have over these guys, the ones that we've used so far? And these are the next ones that we're going to look at. So what advantage does this have? These guys do not make physical contact with what they're trying to measure. So all these are going to affect the flow. They're going to affect the flow a little bit, right? They're going to slow the flow down because they've got to make physical contact with that. So anytime you do this kind of stuff, if you make physical contact with the flow, then of course that means it's going to be what? It's going to slow the flow down a little bit. This guy here will have no effect at all on the flow rate. It does not make physical contact with the fluid that is in motion. So it don't create a difference in pressure. So as soon as you do that, you're going to decrease the flow rate, right? So that will be one advantage of this. Of course, the disadvantage, of course, this would be more expensive than the other ones that we're looking at. The cheapest ones would be these guys right here, that where you have a visual indication of the flow rate, and we're not taking that and converting it over to an electrical signal for a programmable controller or something else. So these two are exactly the same. Ultrasonic flow meters. We have a Doppler effect. So what happens, it depends on the sonic conductivity, the particle density, and the flow profile. So these guys would have to be calibrated depending on what you were trying to measure. These can be affected by temperature, which changes the density of most fluids. So most fluids expand when they heat up, and then they contract when they cool down. So that would change the viscosity of the fluid, which could affect the flow rate. And it's so unsuitable for high accuracy. So these guys right here give us an indication, but they have so many different variables in the thing that their flow rate would not be exactly precise. Time of flight measures the time between flow unaffected by temperature or viscosity. But these liquids are going to have to be liquids or gases. Gases would work really well with this thing, because most gases are transparent, but these would have to be pretty clear liquids to be able. These guys would. I just got a text, guys. I lost my train of thought. These guys would not work with anything that you can't see through. But these guys are very accurate, within 1% of the flow rate. These do not make physical contact with the material, but they do have to work with gases. Primarily, these guys would be used with gases, and we can't use them with slurries. Slurries of liquids that are not They don't have to be totally transparent, but the actual time of flight, it has to be able to go through them, right? So these are both ultrasonics. So are we okay? Non-contact. So here's some ultrasonics. These would be Dopplers, so you can tell the time of flight because these guys are going to be mounted at an angle. Okay. And these guys right here would be permanent. It looks like this is actually built into the section of piping. This guy right here looks like it can actually be strapped onto the side. And this would be Doppler. So Doppler, the transmitter and receivers are going to be on the same side of the pipe, and they're going to be mounted perpendicular. Well, they're mounted perpendicular, but they're not actually that way, right? And then the time of flight, these are going to be mounted at about, looks like about a 45-degree angle. So that's it for flow sensors, guys. Y'all got any questions? Y'all anything you want to go back and talk about? So,
Hey Rich.
yeah.
Hey Rich. Go back to the slide that said damn, I forgot what it just said. The one you wrote on that had induction and all that.
It's probably not up there anymore. Because instead of tabbing through, I keep hitting escape and it won't let me go back to the PowerPoint. This guy?
Yeah. Okay, I'm good. I just needed the print screen of it.
Okay.